So this is the second part of this huge second lecture. So we could call it lecture 3. Okay, so here we'll be looking at network diagrams in a little bit more detail. So we introduced them in the previous lecture. Now we're going to talk about how to actually construct network diagrams. What do we mean by critical path, and how do we identify slack? So it's all about scheduling. So we're still talking about project planning. We're talking about scheduling in particular, and we're talking about network diagrams as a tool used as part of WBS, work breakdown structures. Okay, so this is a short lecture. It looks like we have a lot of slides to cover, but actually most of these are just working out. So just a reminder, we have 2 class tests coming up. We have one in week 6 and one in week 11 in January. Okay, one is worth 15% of the module, one is worth 20% of the module. So even though these are open book tests, you really need to be prepared for them. Okay, so what we'll be covering today will go into both class tests, because the second class test covers the content of weeks 1 to 11. The first class test covers everything until the class test. Okay, so this is just a reminder of where you should be up to in your virtual project. So we'll be looking at how we can use network diagrams. That's what this part of the lecture is about. So we'll talk about critical path and slack, and both of these feature heavily in tests, and this is also where people lose many marks. So don't let that be you. So network diagrams. We've spoken about a network diagram and how it differs from a Gantt chart, but now we need to talk a little bit about some specifics. So network diagrams enables us to identify and potentially reduce project duration by understanding dependencies, identifying overlapping activities, and how overall duration can be reduced. There are two, there are many common approaches, but there are 2 widely used approaches: the critical path method, used in construction projects, and the program evaluation and review technique, PERT. So depending on the industry you move into in the future, you might come across either or both, but we'll be looking at the critical path method. So remember this, we said that there are 3 parameters that we use to calculate the expected time that a task should take. And we said this expected time is the result of adding the optimistic time, or finding the weighted average of the optimistic time, the pessimistic time, that's the respectively the minimum and maximum possible times, with the most likely time, so 4 times the most likely time. We add all these together, we divide by 6, that gives us something called the expected time. Now, in our network diagrams, we will use this expected time, and we'll use it to indicate the earliest and the latest. So that's the E and the L, the earliest and the latest times for an event to start or to finish. So the latest starting time and the latest finish time. We also have the latest event and earliest event time and the earliest and latest occurrence time. And we'll be looking at each of these. So don't let these acronyms scare you. All they are different usages of the expected time, ET or TE. So let's talk about conventions. There are several. There are two common conventions. We'll be using both, one for the task, one for task 2, and one for the purposes of this module and for your examples and the class test, etc. They won't be the same. So there are two common formats or convention. Something called AOA, or activity on arrow, or activity on node. So you've got nodes and you've got arrows. So sometimes we put the activity on the arrow and sometimes we put it on the node. And depending where we put this activity, the shape of our network diagram will differ. So we will be using AOA even though it's being phased out. AON, that's what you'll be using on your tasks. So that's what Microsoft Project uses. So that's what you'll be using for task 2 on Microsoft Project. Now, remember we said there's a node and an arrow. So the node is either a box or sometimes a circle. So sometimes it's represented as a circle, sometimes it's represented as a box. But in either case, there are conventions for that as well. So in Microsoft Project, you have a node with an activity description at the top, a task number, a duration, then a start date and an end date. There are other conventions where you have your earliest start time and latest start time at the top, activity description in the middle, and then duration and slack, whereas here you have to actually calculate the slack. So those are the nodes. The arrows, that's where you will actually see the sequence of activities. This is because we're using AON, so activity on the node rather than activity on the arrow. So this is what a AON diagram might look like. This is using the Microsoft project format. So for example, if you look at this activity, you can see the description. Boring description is simply B. That's the description of your activity. You have your task number, you have the duration, 28 days, you have a start date, and you have an end date. So that's how you'd interpret these nodes. Now, activity on arrow, that's what we will be using in this module. So this is not the Microsoft convention. So here, the nodes have less importance because the activity actually happens on the arrow. So here you have the activity ID, and here you have the expected time. So this is your expected time. So this is your A plus 4M plus B06. This is the actual duration of the task. Now, at the node, we have something called an event label, which could be a number or a letter or a word. And then we have the earliest event time and the latest event time. That can be a date, or it can be a duration from the start of the project. So in this case, event label 1, the earliest it can happen is after 4 days or weeks or months, whatever the unit is, and the latest is 6. So now, for the fun part, now we're going to talk about how we're actually going to calculate the timings. So, let's look at a diagram like this. We can construct this diagram from the table of activities and precedents. We should be able to construct a diagram like this. Once we've created our diagram, we need then to put all the numbers in. So you have event IDs and you have activity IDs. Your activity IDs, remember this is AOA, so the activities are on the arrow. So that tells us, for example, if I look at this arrow here, what does that tell me? It tells me that activity A will take 20 days. Activity D will take 15 days. Activity J will take 8 days. It also tells me that we can't get to this point, i.e. we can't initiate activity J until activity D and E have both taken place. So just looking at this diagram, how long will it take for this project to complete? How long will it take me to get here? What's the earliest completion time and what's the latest completion time? How soon can we finish this project and what's the longest this project might last? So we do this by looking at each of these nodes one by one, and we try to populate these cells one by one. And there's a specific way to do that. So the first thing you need to do is start from the beginning. So you start from the very first activity, and we call that time 0. Now, if you take it activity by activity, your first activity will take 20 days. So therefore, the earliest time we can reach event 2 is after 20 days. Similarly, event B or activity B takes 20 days, so the earliest we can get to here is 20. And activity C takes 10 days, so the earliest we can get to here is 10 days. So that's the first thing we do. So we've got 20, 20, 10. Now, if we go to the next level, so this we started with the first level, 0. That's our first set of activities. Now look at the second set of activities. We need to look at how do we get to event 6. We need to have completed both D and E. So to get to here, we need either 15 days following the 20 days, which is 35 days, or 10 days following the 20 days it took us to get here. So 20 plus 10 is 30. So what's the... How long will it take to get here? If it'll take us 35 days to get here using this route, and 30 days to get there using that route, but we're unable to launch activity J until both this and this have both happened. So what we look for is the larger of the two. We look for the larger of the two. So we actually look for 35. So in here we put the number 35. Similarly, let's look at this. So to get there, we need 4 days following the 20 or 11 days following the 10. So it's either 24 days or 21 days. So we take the larger of the two, 24. So 24 goes in there. And we do the same for our third level. So in order to get here, we need 8 days following 35. So that's 43. Or we need 14 days following 20. So that's 34. Or we need 18 days following 24. So that's 42. So we take the larger of those. So now that's the earliest time this project can complete. We can't reach this point. We can't complete before 43 days. So this is the earliest ending time. So this is what we call our EET, earliest event time, or earliest completion time in this case. Okay, so what do we put in these spaces here? These are the latest event times. So we've already said that this is going to start at 0. But what do we put in the remaining spaces? Well, just like we put a 0 in our first box, we put the same EET as a LET. So your LET here, your latest time, will equal your EET. Okay, these are the same. But that's only for your final level. This is for our final event. Now we need to go backwards and say, well, what goes in there and what goes in there? So now what you need to do is you need to subtract. So you have your 43 days. If you take away 8, that'll give you 35. 43, take away 18, that'll give you 25. And you can go back and do that again. 35, take away 15, and then 35, take away 10, and then 25, take away 11, 25, take away 4. So that's where we get the 21, 14, 20, etc. So now all our numbers are identified. We have the earliest and latest time for each event. So we have the LET and the EET for each event. Now we want to talk about something called Slack. Now some books refer to it as float. They are the same thing. So Slack and float are the same thing. So Slack is an amount of time that a project can be delayed without delaying either subsequent task completion or the overall project completion. So you have something called free slack for an event or a total slack. So for each task, the difference between the LET and the EET, that is your slack for that task. Obviously, if these two are the same, then you'll have zero slack or zero float. But if there is a difference, that is the amount of slack you have. So for example, here we have zero slack because 20 minus 20 is 0. But here you have 1 day. Here you have 1 day of slack. Here you have 4 days. Here you have 1 day. What does that mean? It means that here, even if we are delayed, even if that task is delayed by 1 day, it won't affect the overall project completion. Well, let's try to think about that. So it takes 10 days to get to this event here. And it takes 11 days to get to here. So we are allowed a delay of 4 days simply because it's taken 20 days to get to here. So it's going to take 24 days to get to there anyway. So even if there's a 4-day delay, you have 10 plus 4 plus 11, it'll still be 25. So even if we have a delay in getting to here, that won't delay this, and therefore it won't delay the total EET or LET. So we can identify the slack simply by looking at where we have a different LET and EET. Okay, so it's not so easy when you use AON, like a Microsoft project, but you can deduce it from a Gantt chart very easily. And there are tricks you can use to get MS Project to show you the slack. Okay, and as I said, task 2B is all about slack, identifying it and identifying the critical path. Now, what do we mean by a critical path? Critical path is something project managers need to identify in order to identify exactly how long a project will last. So critical path is those tasks or those activities which add up to the longest overall duration. So that determines the shortest time possible to complete a project. Now you might be thinking, longest duration, shortest time, how does that work? Well, the shortest time possible is determined by the longest, the tasks which take the longest, because a project can't happen faster than the slowest part. So by identifying which bits take the longest, that allows you to find the shortest time possible. So you want to find something called the critical path. Now sometimes there can be more than one critical path. Now if you have a critical path, then any delay on an activity in the critical path will affect the completion date, because by definition the critical path determines the shortest time possible to complete the project. So any delay on the critical path will affect the earliest completion date. So remember, the critical path is the path of longest duration. So there will be other paths. So these will be non-critical or subcritical. Now the time it takes for the critical path is called the critical time. So the critical time is simply the time of the critical path. Therefore, it is the shortest time possible to complete the project. So let's look at this network diagram. This network diagram is slightly different in the sense it is activity on arrow, but what we've also done is use the horizontal axis to indicate time. So here, the length of the arrow will indicate the duration. So remember I said that these diagrams, they're often drawn from tables, or from the diagram we can create a table. Both are possible. So let's have a quick look at this diagram. We have a set of activities A, B, C, D, E, and we have precursors or precedents. So A doesn't need anything to have happened before it, but activity B can't happen until A has happened. C can't happen until A has happened. So activity A, remember it's activity on arrow, so this is the activity. It's on the arrow. Activity A doesn't need any previous activity, but B can't happen until after A has happened. C can't happen until after A has happened. D can't happen until after A has happened. And E has to follow B. So E has to follow B and therefore comes after A as well. Now, if we put these durations onto the arrows, now we have an activity on arrow, where the length of the arrow indicates the duration. So from this, how long will the project take? Let's say we're arranging a wedding party. How long will planning this take? It looks like it'll take 8 days, simply because we can't get to event 6 until after this has happened, E, and E can't happen until B has happened, and B can't happen until A has happened, and if you add 3 plus 2 plus 3, you get 8, and we call this the critical time. So 8 is the critical time, and this is called the critical path. So your critical path is ABE, ABE. That's your critical path, and your critical time is your 8 days. We've added a fourth column here, which is the cost. Now, if you add the cost of each of these activities, or you have to include all the activities, that'll give you your £120. So it must be a really budget wedding, but there you go. We've planned our wedding. The planning takes 8 days. It'll cost £120. Now, let's say we didn't have 8 days. Let's say we wanted this to happen in 6 days, in 5 days, in 4 days. Let's say we wanted our event to happen within a given time. Let's say you didn't have 6 months to build a hospital, you needed it built in 8 days. What do we need to do? Something called critical path analysis. This is where activities are prioritized. And this allows you to shorten the critical path. There are 2 ways of doing that. Well, I've listed 3 here. Pruning critical path activities. That means you start eliminating activities. We'll say, okay, let's cancel activity B. Let's cancel activity C. It's not essential. Another way of doing it is by fast tracking. Fast tracking is by doing things in parallel. So you might previously have said, well, B can't happen until A has happened. Fast tracking is saying, okay, let's just get B and A started at the same time. Even though B would normally have come after A, let's just start them at the same time. And by fast tracking, we end up with a shorter critical path. But there's a third way, which is called crashing the critical path. And crashing the critical path means actually shortening the durations. It means making these arrows shorter. How do we do that? How do we actually shorten the arrow? Well, normally we throw resources at it. That means there's an extra cost. So we spend some money for things to happen faster. So, for example, the caterer might have said, look, it's going to take 3 days to prepare all the food. But I can do it in 1 day if you pay me extra. So that saving there, those 2 days, that's by how much we've actually crashed that task. So each task or each activity can be crashed, and if those activities lie on the critical path, that will result in a shortening of the critical path and therefore a reduction in the critical time. So another little video for you that illustrates this difference.
So when we refer to fast tracking and crashing, well, those are 2 techniques, but I mean, well, we were supposed to do activity A and then we're doing activity B. Well, in this case, we've actually decided that it's best that maybe they both happen at the same time, or we're going to start B just slightly before we were supposed to start A. So in that case, we would have then 2 things happen almost concurrently or simultaneously, and that's what we would refer to as fast tracking. Now, the other one is crashing. That crashing technique means you are throwing more things at it, like more resources or more budget, more costs, more people, whatever it might be, to speed things up. So obviously that one costs money. And you could do both in tandem or a variation of each. But these 2 are what we use to compress the schedule, to maybe speed things up, maybe to meet deadlines that are fast approaching, or maybe we're just behind and we gotta catch up. So that's the fast tracking and crashing.
Okay, so he basically was a cartoon character saying exactly what I just said. So we're going to look at the same example and see how many ways we can actually crash the critical path. So to do that, remember I said crashing involves doing an activity in less time than it would normally take, and that's going to cost money. So we need to know a cost per day or a cost per unit. That it could be per hour, per week, per month, but we need to know a cost per unit, and that'll help us decide 2 things: if we're going to crash the project, because we might not be able to afford it, and where exactly to crash it, i.e. which activities we're going to crash. So that'll determine whether crashing is going to happen and what the total new critical time will become. So back to our example. This time we have an additional column where we have not just the cost, you've seen that. Now we've added the crashed cost. And instead of just having the normal duration, we now have a crash duration. So what does that mean? If we look at the first row there, it means activity A normally takes 3 days. So that's your 3. Activity A normally takes 3 days. And it normally costs £40. But it can be done in 2 days. But that would cost an extra £80. Or it would cost £80, so that means an extra £40. What about activity B? Activity B normally takes 2 days. It would cost £20. It can be done in 1 day for £80. So for extra £60, it can be done in half the time. So clearly, activities A and B don't cost the same to crash. So activity A, we're reducing the time by 1/3 for twice the price. Activity B, we're halving the time, but we're multiplying the cost by 4. So activity B is much more expensive to crash. So we have something called a crash cost, or a cost per day. So if you subtract 80 minus 40, and you divide it by 3 minus 2, that'll give you your cost per day. So 80 minus 40, that's your crash minus normal cost. Divided by 3 minus 2, that's your normal minus crash time. That'll give you the cost per day. So remember, our critical path was A, B, E. And we want to reduce that 8. So what should we crash? Should we crash this? Should we crash that? Or should we crash that? Which activity should we be crashing? So you need to do the calculation and see how much crashing each activity would cost. So 80 minus 40 divided by 1 is 40. 80 minus 20 divided by 1 is 60. 50 minus 20 divided by 1 is 30, etc. So now we have this third column, or this fourth column of cost per day. So we've now calculated that. Now we know that it will cost us £40 to reduce that by 1 day. And our critical path is ABE. That's our critical path, ABE. So there's no point looking at crashing C and D. All we're interested in is A, B, and E. So that's A, that's B, and that's E. So which of those should we be crashing? It costs £40 per day to crash A, £60 per day to crash B, and £35 per day to crash E. So it looks like E is the cheapest to crash. So that'll bring this activity to there. It means we'll have our wedding ready in 7 days instead of 8. Okay, so we choose to crash task E simply because E is the cheapest to crash. So that would bring this activity to here. So this is our crashed diagram. Here we've crashed task E. We've crashed E. So we no longer have anything happening here because this has been reduced from 3 days to 2 days. It's possible to crash it further to 1 day, but we've chosen for this first step to crash it by 1 day. Crashing it a further day might not help And why is that? You might notice that there's now two paths in red. There's A, B, E, which is my critical path. 3 plus 2 plus 2 equals 7. But now 3 plus 4 also equals 7. So now we have two critical paths. We have this critical path and that critical path. So there's no point crashing E further because that wouldn't help my path AD. So now we have two critical paths, ABE and AD. So if we're going to consider crashing further, we need something that's common between both of these paths. What's in common? A. So it makes sense to look at A. Even though it's cheaper to crash E, but crashing E isn't going to help because activity or event 5 still takes 7 days. Similarly, crashing D isn't going to help, even though crashing D is really cheap. It's just £10 to crash D. But crashing D is not going to change event 6. But crashing A can bring everything back. So we can crash A by 1 day at a cost of £40, and that will bring everything back. So here, A has been crashed. What have we crashed? We've already crashed E. Now we've crashed A as well. It's cost us £40, so the price has now gone up by £40. But what's happened to the duration? We now have our wedding party ready in 6 days. Now we need to check how many critical paths do we now have. We still have just two paths. We still have 4 plus 2 is 6, and 2 plus 2 plus 2 is 6. Can we crash it any further? So we can no longer crash A anymore because the minimum time was 2. So what can we now crash? We'll either crash B and D or E and D. But it's essential that it's D and something. So if we were to crash task D, that would cost us £10. And that would bring this event earlier by 1 day. But we would then also need to consider B and E. B is the most expensive to crash, so it doesn't make sense to consider B. You'd want to crash E further. You're allowed to go all the way down to 1 day. Now, if that wasn't possible, then we wouldn't be able to do that. So this is the result of now crashing D. D, we've reduced it from 4 days down to 3 days. And that 3 days has cost us £10. So 195 has gone up to £205. But that hasn't changed the duration of the project, has it? The project is still 6 days. So crashing D on its own hasn't helped. And the reason is because there are two critical paths. We've got that critical path and that critical path. So A, B, E, and A, D. And now we've only reduced one of them. That hasn't affected the total project duration. So we still need to crash one more task. And that's either going to be B or E. And we'd look at which of these is cheaper to crash. And clearly it's E. So for an extra £35, we can bring this task back 1 day. So there, we've added £35, but by crashing task E again, there, we have now brought the project back by 1 day, and in total it's gone back by 1, 2, 3 days. So that is a successful crashing. Is there any more crashing we can do now? We still have two critical paths. We still have A, B, E, and A, D. We can't crash A anymore because 2 is the minimum. We can crash D because D can happen in 1 day. So in theory, this can go back all the way to here because D can be crashed to 1 day. But B can only go to 1 day, and E has a minimum of 1 day. So the only thing we can do if we want to further reduce the time is to crash both B and D. So that is possible. If we crash B and D, that'll bring everything back by 1 further day, and now we've saved that day. In effect, in total, we've saved 4 days. But look at the cost. The cost has shot up to £350. So that's quite expensive because B was really expensive to crash. So D wasn't, but B was. So now if you put all of those costs and durations into a table or into a graph, you can now say, well, my original wedding was supposed to happen in 8 days and cost that much. By crashing one task, it cost me a little bit more. I think it was £35 more, and it saved me 1 day. But I can go all the way to 4 days. I can crash it by 4 days with essentially all tasks being crashed. But what effect will that have on the cost? It'll bring my super budget wedding up from £120 to £350. So that's a big increase in cost. So your project manager will have to scrutinize a graph like this. We'll be looking at that very carefully, and then we'll need to decide where on this graph am I comfortable? Am I happy with where I started, or do I want my project to finish earlier? Am I prepared to part with all this extra cost in order to save this much time? So sometimes project managers need to do this. Let's say a mobile phone manufacturer, say Samsung, needed to launch their new mobile, their latest Galaxy, and they had already set a date. Let's say they wanted to launch their new Galaxy flagship at an event in September 2021. Now, if after looking at their critical path, it looks like the time it'll take to actually launch their product isn't any good for them because it's 2 months too late, in order to save 2 months, remember the 3 things they can do? They can either prune, fast track, or crash. So let's say they end up needing to crash. That means they need to spend a lot of money. How much money they spend really depends on how much time they want to save. So they need some kind of a graph like this in order to, a project manager needs to be able to look at a graph like this in order to determine, well, how much am I prepared to pay for this reduction in overall time. Okay, here are a couple of examples, but in the interest of time, I will set these as homeworks for you. So this is homework for you. You don't need to submit it. It's just a useful exercise for you. It'll help prepare for your class test. So think of how you'd use an activity, precedent and duration to create a network diagram, find the critical path and the slack for each activity. It's really straightforward. If you ever get stuck, the solutions are here. And I can show you how we got there, but it's really straightforward. So that in red, that's your critical path, and the slack is identified there. Here is another homework example. Again, similar kind of question, network diagram, critical path, critical time. And here's the solution. You can do that. You can get there on your own. That shows you the critical path. And finally, another homework example. I can go through these and I can upload the solutions for you, or how I got there, but really it's fairly easy. So here you have your activities, your precedents, crash time, crash cost, and you need to find the cost per day or the crash cost per day using these numbers. And again, here are the solutions. Okay, so finally, to conclude this lecture, just a reminder of where we are. We just completed lecture 3, which was the second of a 2-part lecture. So we've done those 2 elements. You will have finished task 1, and you are now starting on task 2. You finished task 0. Hopefully you will have finished the resilience questionnaire. The next things to focus on are the class test in week 6 and the next 2 employability events. But your immediate concern should be task 2. So that's for the next 2 workshops on the next 2 Fridays.